thanks a lot for the invitation and for coming to the talk. So this is based on joint work with Thomas Lamb and separately with Terence George, who, so Terence George is a postdoc at UCLA. I can see Terence. Raise your hand. Yeah. So Terence is over there. He's a postdoc. He's going to be looking for jobs next year. So, he's amazing. Please be nice to him and invite him to your seminar, talk to him, etc. And yeah, so I was preparing the slides, but after a few Beamer slides, your mind kind of starts to wander. So I made a game instead. So you're all welcome to scan this QR code and play during the talk, and it's going to be equivalent to listening to the talk. So you really. So here's the game. You click on blue circles. When you see a green circle, that means it's good. So you click on that, and the goal is to get rid of all the crossings. And then level 2. So again, so there's like 50 levels for you to. Yeah, I don't have that many slides, but yeah. So let me finish this one. Okay. Okay. Yeah. Success. So level 3. Sorry. So yeah, I mean, feel free to really. You're gonna understand everything from just playing the game. So okay. I mean. Is it procrastination? I don't know, maybe, but at least it was fun. So yeah, I'm going to just cover a lot of background. So basically, there are these two objects in my title. So move-reduced graph on the torus and positroid Catalan numbers, and they're all somehow, there's two different problems which look completely separate, but they reduce, both of them reduce to the same problem about affine permutations. So I'm mostly going to be talking about affine permutations. And here's the definition. So an affine permutation is a bijection from Z to Z, which is n-periodic. Just like in this picture here. So this picture is 8 periodic. And so you can consider two interesting sets of examples of affine permutations. So this is a big one. Here's a very small one, just a simple transposition. So you swap 3 and 4, and then you do this for 3 plus n, 4 plus n, etc., kind of periodically. And another example is this affine permutation called lambda. So this picture is lambda squared, but lambda just sends I to I plus 1. Okay, so that's also an example of an affine permutation. And so the claim is that these two types of permutations generate the entire group of affine permutations. Okay, so these SI generators here, they form a Coxeter group, affine type A Coxeter group, but then this lambda gives you like an extended affine Weil group or something like this. Yeah, and because it's basically a Coxeter group, there is the notion of length, which comes from Coxeter groups, and so yeah, the length is the minimal number of generators of SIs that you need to express your F. But in other words, it's also the number of affine inversions of your affine permutation. So an affine inversion is that basically it's a crossing. So let me show you an example. So here's an affine permutation of length 6 because there is, if you count. So you count the crossings modulo n, right? So you count crossings inside a single fundamental domain. And so there are 1, 2, 3, 4, 5, 6 crossings. So the length is 6. And so the goal of the game is to bring the length down. So that's your target. You want to bring it to the target number here, which is 0 in this case. Yeah. And so, yeah, so these are kind of very classical. Let me now give a sort of much less well-known definition. So two affine permutations are called C-equivalent if you can get from one to the other by clicking on only blue circles. And by that, I mean, so clicking on blue circle means you apply a simple conjugation, right? So you conjugate by one of these SIs in such a way that the length is preserved. So when you conjugate, the length is either go up by 2 or be preserved or go down by 2. And in this game, you're never allowed to may increase the length. So the length can never go up. It can only either stay the same, in which case the circle is blue, or it can go down, in which case the circle is green. So, but if only blue circles, so you click on a bunch of blue circles, those moves generate C equivalents. Okay, and so I also want to define some kind of, if the length goes down, then I'm going to denote it by this C arrow. So F maps to F arrow F prime. If you can get from F to F prime by clicking on either blue or green. So you apply simple conjugations in such a way that the length always weakly decreases.
If you add red disks in the empty spots, it would increase the length by 2.
Yeah. So when you conjugate, you kind of swap 8 and 9 at the bottom and at the top, right? So if you swap them at the bottom, these two arrows are going to cross. And similarly, at the top, like these two arrows are also going to cross. So so the length is going to increase by 2. And those are not allowed in the game. And so finally, F is C-reduced if its length is already kind of minimal possible. You can never bring the length down by clicking on blue circles. Okay, so maybe an example here. Oops. So this is not C-reduced. If I click, then this is C-reduced. So no matter how much I click on blue circles, I can never find another green circle for me to click. Okay, but there are still some crossings here, but yeah, you can never bring the length down anymore. All right, so that's kind of the C-reduced and C-equivalent are going to be the key notions for this talk. So let me know if you have any questions on these. Yeah?
Did you say what the green dots are?
The green dots are the moves where the length decreases by 2. So like for example here, if you swap 16 and 17, you're going to remove this crossing. But if you swap them here at the same time, you also remove this crossing. So that's where the length goes down by 2, for example. Any other questions? Okay.
Right, so these are all conjugacy preserving moves. Is there an easy description of the conjugacy classes here?
Yeah, well, sort of. But yeah, the difficulty is that these are not all possible conjugacy preserving moves. So the conjugate classes are bigger, and yeah, so there's a subtlety of like, but describing just the conjugacy classes is easier. It has been done before.
Okay.
Yeah.
Is it obvious that there's no advantage of going up to get maybe further down?
Yeah, that's a good question. So like maybe you can bring the length even more down if you first went up and then went down a different way, and so that turns out to never happen, but it's very tricky to prove. Any other questions? All right. So yeah, now the main 2 questions that I'm gonna look at in this talk are, so question 1 is which affine permutations are C-reduced? And question number 2, which C-reduced affine permutations, so which pairs are C-equivalent? Yeah. And so to answer these questions, I'm going to have to introduce a little bit more notation, so but very slightly more. So first of all, any affine permutation has an integer k associated to it. It's defined by this kind of average of fi minus I, which is unclear that it's an integer, but let me show you another example. So it's basically the number, so you make any vertical slice of your diagram, like for example here, and you count how many arrows cross it from left to right, minus how many arrows cross it from right to left. You kind of measure the flow through the vertical cut, and it doesn't matter which vertical cut you take. Like here, you always get 3 arrows from left to right, and so k is 3. And here, k is 0, so no matter, so like for example here, there is 1 arrow from left to right and one from right to left. But here, between the two green circles, there is 2 arrows from left to right and 2 arrows from right to left. So either way, k is 0. And yeah, so let me denote by skn, just the subset. So my group of affine permutations splits into these different copies for different values of k. They're all kind of in easy bijection with each other, but yeah, there's different pieces. And so finally, let me define the cycles. So I'm gonna, as you can see in these pictures, these arrows are colored in different colors. And these colors correspond to cycles of basically, if 14 is green, then f of 14 should be green, and etc. So more to be rigorous enough, so you take your affine permutation and you look at it modulo n. So f bar is my permutation modulo n, and so defined by the condition that it's a reduction modulo n. And then number of cycles of my affine permutation is by definition the number of cycles of its reduction modulo n. All right. So now I'm going to try to state a theorem. Right? Yeah. Let me just state the theorem. Which we proved with Terence, building on a bunch of other works. So there's, so see also, we have a paper with Thomas Lamb, and there's a paper by Timothée Marquis, which is proves something that's very close to what we proved. And also He and Ni. And so there's old work of Geck and Pfeiffer. These people in Coxeter group theory, they're studying like irreducible characters of Hecke algebras and things like that. And so they end up with the same kind of game that I'm showing you here. So the theorem is that, first of all, an affine permutation is C reduced if and only if its length is minimal possible. Minimal possible in the conjugacy class. So it's a non-trivial statement, and that happens if and only if. So explicitly, each cycle G of f. So every cycle is itself an affine permutation. If you pick, let's say, the red color here, you just restrict to all the red numbers. You're going to have some kind of n prime periodic bijection between the red numbers, where n prime is a number of, like in this case, n prime is 1, 2, 3, 4. Okay, so each cycle, let me maybe write G belongs to S, K prime, n prime tilde, has exactly d of G minus 1 self-crossings where actually, let me have some separate place for notation. So if G belongs to S tilde K prime and prime, then d of G is the GCD of K prime and n prime. Okay. Yeah, I'm sorry to make you tilt your head back and forth, but yeah. So every cycle should have this many crossings. And the second condition is that any 2 cycles, each 2 distinct cycles, G1 in S tilde, K1 and 1, and G2 in S tilde, K2 and 2 of F have to cross exactly the determinant, the absolute value of the determinant K1 and 1, K2 and 2 times. Okay? That is the first part of the theorem. And maybe in this example, so let's just do an example. So here I have the red and the green. Right? So the red, what is k and n for the red? Maybe somebody can tell me. N is 3, for n is 4, and k is 0. Yeah, so you take a vertical line and you look at the red arrows which cross the vertical line. So k is -1. -1, 4. And then the green is, what is green? 1, 2. Okay. Okay, so you take the determinant and you get, well, absolute value, 6. So you look at this picture, there is more than 6, or is it 6? Yeah, there's 8 crossings in this picture. So, but once you press on the green circle, you get 6, success, right? So yeah, that's kind of part 1 of the theorem, which is the easier part, but still very hard to prove. And if you're playing the game as I'm speaking, you're going to see why it's hard, because like most of the time you just see a bunch of blue circles, you don't know which one to click, like what's the strategy that is going to help you play the game. And especially if you go to one of the hard levels, like level 50, it's going to take a while. And so let me try to state the second part of the theorem, which is also, it's much harder, basically. So the second part is that f and f prime, so let f and f prime be two C-reduced affine permutations. Then f is C equivalent to f prime if and only if the following two conditions are true. So the first one is that, let me just state it and then I'm going to explain what it means. So the
I wonder if you could turn on the light over the boards, because it's a bit hard to see.
Oh, yeah, the light. They turned this light on, but oh, you can't see what I'm writing. That's too bad. Is it better? Okay, great. Thank you, Alejandro. So yeah, so the first condition is that the cycles, we'll just write cycles of each slope give the same cyclic compositions for f and f prime. So what do I mean by that? First of all, yeah, I guess this part is not visible anymore. So again, d of g was the GCD, k and n, and g belongs to s prime, s tilde k comma n. And the slope is by definition just k over n. So for each cycle, you have a slope which is just k over n. And so, yeah, maybe let me show you an example. So first of all, yeah, so here's a cycle which is C-reduced, right? So here k is 3 and n is 9. And that's basically an example for that part of the theorem. So it has GCD minus 1 crossings. It has 2 crossings, right? And you can't really bring this down. No matter how much you click on the blue stuff, you can never get rid of those 2 crossings. So yeah, so this is really the minimum possible value. And so if you have several different cycles of the same slope, like in this picture here, right, so there is a whole bunch of cycles of slope 0. Right? So k is 0 for each of these cycles. And so you can never really swap them. The cyclic ordering between the sizes of these cycles. Right. So if I just write down the kind of this composition of the sizes, right? So in this case, the composition would be like 1, 3, 2, 3. Okay. Alpha is 1, 3, 2, 3 for cycles of slope 0 in this affine permutation. So the claim is that this is an invariant under C equivalence. Okay, you can never swap two cycles of the same slope if it's C-reduced, because they never cross each other by the determinant formula on the other board. Yeah, so the cyclic composition should be the same, and it turns out that this is not enough, that there is a subtle other invariant. So it's going to look very weird, but it's there. You can never get rid of it. So the modular invariants for f and f prime should be the same, where mu of f belongs to z modulo dz is the modular invariant. Modular invariant. And here d is the GCD of all cycles of d of g, where g is a cycle of f. Okay. I mean, you don't really have to pay attention to this. You just the only thing you need to know is that I'm not even defining this, but just there is this GCD related invariant that if it's different than the two permutations, you cannot get from one to the other. And so I can show it to you in this example here. So here the GCD of all, there's only one cycle. So the GCD of all cycles is 3. And so you can never relate this cycle to its cyclic shift by 1. You can relate it to a cyclic shift by 3. Right? So here 1 goes to 6. If I press here, then 4 is going to go to 9. Right? It's a cyclic shift by 3. But I can never, the things in between, I can't really do this by blue, quicken on blue. So yeah, so that's the full characterization. That's the basis for the rest of the talk. So yeah, any questions up to this point? Yeah.
Do you have any sort of, I guess, hopes about characterizing it in terms of other invariants, maybe absolute length or pattern avoidance or something like that?
Yeah, we haven't looked at those in particular. Yeah, but I think regardless, there has to be some kind of GCD. So pattern avoidance has no GCD inside of it, right? Or yeah, so whatever you do, and we found some papers with incorrect results, and it's easy to spot incorrect results if they claim something and there is no GCD. If there's no GCD, you know where to look for mistakes. So yeah.
So when k is 0, are these the permutations without lambda?
Are these permutations what?
Generated by things without using lambda.
Yeah. So without lambda, you get all things with k equals 0. Yeah. Any other questions? All right. So okay, that was the affine permutation part, where I had one slide for the entire duration. So now I'm gonna talk about the two applications of this stuff. So the first application is bipartite graphs on a torus. So people in statistical mechanics love these objects. Many people in this workshop love it. So you put a bipartite graph on a torus, and so you study maybe the dimer model on this graph. And so the fundamental invariants of the dimer model are called these zigzag paths, or strands, or whatever, where these are paths in the graph where you make a sharp right turn at every black vertex and sharp left turn at every white vertex. So there is these zigzag paths are an easy way to define the Newton polygon of your bipartite graph. Right? There's two ways to get the Newton polygon. One is to just record the homology classes. Every zigzag path is a closed loop on the torus. It has homology, which is an integer vector in the plane. So yeah, if you just record them counterclockwise, you get the Newton polygon. And another way to get the Newton polygon is to take the dimer partition function on this graph. It's going to be a polynomial in 2 variables. So you take the literal Newton polygon of that polynomial, and you get the same object here. Yeah. So here's the definition from Goncharov and Kenyon that a graph on a torus is minimal if it has twice the area faces. So for example, here twice the area is equal to 2. Here's the number of faces is 1, 2, 3. So this twice the so this is 1/2. This is 1/2. So twice the area is 2. Yeah, but not twice. Yeah. Yeah. So twice the area is 2, and the graph is not minimal. Yeah. According to this definition. And if you remove this edge, then it becomes minimal. So great. That's a definition. And also, people in the dimer model study moves for such graphs. So first of all, 2 graphs are move equivalent if and only if. By the way, I have all the stuff from previous slide written down here in case you want to go back to it. So there's C equivalence here, and it should be vaguely similar to the move equivalence here, where 2 graphs are move equivalent if they're related by these kind of standard square moves, urban renewal kind of things. And a graph is move reduced if you cannot, so there are some reduction moves, so all of these moves preserve the dimer partition function. And, but if your graph can be reduced, you replace edge weights A and B by edge weight A plus B, something like this. There's edge weight preserving bijection on dimer model. And so a graph is move reduced if you can never apply a reduction move to any graph move equivalent to this one. Okay? So that's sort of a natural definition, especially if you know about like total positivity and planar graphs in a disk, you know that there has been work of Postnikov and others where it's natural to consider graphs which can be no longer move reduced. And so what happens on the torus? On the torus, Goncharov and Kenyon proved that if your graph is minimal, right? Remember, minimal means that number of faces is whatever, twice the area. Then it is move reduced. And moreover, any 2 minimal graphs are move reduced if and only if they have the same Newton polygon. So it's a complete invariant under these moves for minimal graphs. Yeah. And so minimal graphs are very nice. Goncharov and Kenyon define these cluster integrable systems. So yeah, if you care about integrability, then minimal graphs are your friend. And but the question is, what happens if, I gave a definition of move reduced. Is minimal the same as move reduced or not? Like, is the converse of this implication true? Well, so the answer turns out to be no. These are different objects, and so one way to see, like this graph here is minimal, but this graph is not minimal, but is move reduced. Somehow still, this is move reduced. Like you can play this game. You can apply a square move here, see what happens, you get the same graph. You can never, there's 2 square faces, the square moves take it the same graph, no matter what you do. So it is move reduced, but not minimal. And so now there's a natural question, which Terence and I studied, which is then when are 2 move reduced graphs move equivalent, and what are the move reduced graphs on the torus? Right? That's the motivating question, and let me tell you the answer. For any zigzag path, so similarly to here d of g was the GCD. Here, d of g is d of a zigzag path is going to be also the GCD of the homology vector. And so the theorem is that a graph is move reduced if and only if it has twice the area as before, so that's the minimal part, plus the sum of GCD minus 1 over all zigzag paths. So this is kind of remarkably similar to d of g, this sum over here. Okay, yeah?
So how do you define the homology of a zigzag path?
So it's a closed loop on a torus. So it has homology. Oriented loop, yeah. And the second part, which is supposed to parallel the second part over here, is that two graphs are move reduced if and only if, first of all, they have to have the same Newton polygon. Two move reduced graphs are move equivalent, sorry, if they have the same Newton polygon, and the cyclic compositions that I discussed over here, for any edge of the Newton polygon, there's going to be many parallel zigzag paths, and so the cyclic composition they form is the same, and also the modular invariant. So somehow, nobody has looked at this. Somehow, for every bipartite graph on the torus, there is the subtle modular invariant, which keeps track of whether this graph is move equivalent to some other or not. So I'm going to show you some examples, but basically this part is literally parallel to this part somehow, even though the problems look completely unrelated. So let me try to show you some examples, because this may be unclear. So example number one, as I said, this is minimal, that is not minimal, but both of them are move reduced. And so the reason is that, so I'm putting the cyclic composition for each edge. So for this edge, it has length 2. So here are two different zigzag paths with the same direction. But for this edge, there's only one zigzag path of homology, like -2, 0. So the two cyclic compositions are different, and this one contributes an extra 1 in this summation.
Is there a video game for this one?
Well, in progress, yeah. I finished the previous one at like 7 a.m. today, so it's all right. So another example. Here are two graphs. One is disconnected, another one is connected. And you look at the zigzag paths. The Newton polygon is the same. The cyclic compositions are the same, but they're not move equivalent because one is connected and another one is not connected. So the only difference between them is the modular invariant. So you can see the GCD of all these numbers is 2, and so it turns out the modular invariant is different for these two graphs, and so that's why they're not move equivalent to each other. Yeah?
Does lambda cycle the modular invariant of F?
Say again.
Does lambda applying the cyclic shift increase the modular invariant of F by 1?
Yeah. So for a permutation, if you conjugate by lambda, then this is going to increase by 1. But it's a great question. So for the torus, though, this equivalence includes cyclic shifts in vertical and horizontal direction. And still, this modular invariant somehow is preserved under that. Yeah, it's weird. I'm going to explain this, but this is really an invariant under any kind of stuff you can do to graph on the torus. If they have different modular invariants, then they're really different like this. And so here's another example where, so again, the two graphs have the same Newton polygon, and they only differ in so this edge was moved down by 1 step, and everything is the same except for the modular invariant again. So I challenge you to, without looking at this, to decide whether these two are move equivalent or not. This is, if there was a video game, you would click a lot of times, and then then you don't get that there. What do you do? It's unclear what to do. But now you can just measure the modular invariant. All right. So you look at these pictures, you see that I put some kind of words here. So let me explain how this relates to affine permutations. So basically, let's say you pick any word in this alphabet, right? So you have two commuting sets of generators, SI and SI bar. And so they commute, and so you pick any word, for example, here is one such word, and then you associate bridges. So to each SI, you associate a white-black bridge between I and I plus 1. To each SI bar, you associate a black-white bridge between I and I plus 1. Does that make sense? And to lambda, you associate this kind of Dan twist of the torus. And so you get the bipartite graph on the torus. So any such word.
This is not, like, well, maybe it's bipartite, but that's not the bipartite.
Oh, sorry, yeah, it's not, yeah, so you're supposed to put an extra white vertex between, yeah, or you can contract all the unicolored edges. Yeah, there's different ways to make it bipartite, but yeah, thanks. So, yeah, and naturally, this construction, you can associate to two different affine permutations. Basically, you can ignore the SI bars, and you can get an affine permutation F, or you can ignore the SIs, and then you get the affine permutation F prime. And so the meaning of these affine permutations is, if you look at zigzag paths, so in this graph, all zigzag paths are either going to go from left to right or from right to left. And the ones that go from left to right are, so this one turns left at white, right at black. So the rules, right, make a left turn at white, right turn at black, are such that this zigzag path from left to right is going to ignore all the SI bars. So SI bar is just going to pass without anything. But the SIs is going to apply simple transposition. So really, F is recording on the zigzag paths which go left to right. F prime is recording the zigzag paths that go right to left. And so a theorem which we proved, which this idea kind of appears in Fock and Marshakov, but they just assume that your graph is of this form. But we proved that if you give me any move-reduced graph on the torus, then I can, after some moves, I can put it in this form. Which is, yeah, that part involves a lot of work and is not really in the literature somehow. So yeah, basically, the study of move-reduced graphs boils down to the study of pairs of like independent affine permutations which are C-reduced. So that's how the theorem reduces to the theorem here. And so to answer the question, the modular invariant of the graph is the difference of two modular invariants. So if you shift both of them vertically, the difference stays the same. And so yeah, cyclic shifts don't matter. And those simple conjugation moves really correspond to like moving bridges from one side to the other, or canceling. If you have two of the same bridges on the two sides, you can kind of cancel them, and that's where the simple conjugations come into play in this problem.
Sorry, can I ask, at the risk of saying something stupid again?
Go ahead.
Can all bipartite graphs on the torus be constructed this way?
Well, so not all of them. So yeah, first of all, yeah, only the C-reduced ones. So you can start with, you can give me any graph, and then I'm going to apply some moves, and I'm going to apply some reduction moves. And after some reductions, I can bring it in this form. So yeah, all the interesting ones can become, yeah. Any other questions? Yeah?
Like, what freedom do you have in these two words and the two alphabets?
Yeah, I have a lot of freedom. Yeah, I can choose like a different direction and construct the two permutations this way. So it's, yeah, if you have a Newton polygon, you can pick sort of any orientation. And so one affine permutation is going to have cycles of these slopes, and another one is going to have cycles of the opposite slopes. So like by choosing a different direction, yeah, there's a lot of freedom of how you can represent this graph in terms of these f's. Yeah, and yet somehow we were able to tell precisely which ones are move equivalent to each other, despite this extra freedom. Any other questions? All right. So finally, let me talk about positroid Catalan numbers, which again is going to sound completely different, but the answer is going to be the same. So reminder, S tilde Kn is you look at affine permutations where K is fixed. And so here's a definition, which is due to Knudsen, and Speyer. So they considered a set of bounded affine permutations, which by definition is every value has to be between I and I plus n. That's it. That's a bounded affine permutation. And so there's some geometry. Some people here like geometry, so here's an explanation. You don't have to follow it if you don't know what it is. So the Grassmannian is subdivided into open positroid varieties, which are labeled by bounded affine permutations. So yeah, this set kind of, even the Brugge order arises from the positroid stratification of the Grassmannian, which comes from total positivity. And so a slight technical note, I'm going to be not looking at these, but at these varieties modulo the action of diagonal matrices. Doesn't really matter. And yeah, so here's a main definition for the rest of this talk. You start with a bounded affine permutation, which is a single cycle. Right? So the single cycle condition has to do with so this action, the T action is free whenever your permutation is a single cycle. So if the number of cycles is 1, we define the positroid Catalan number in two different equivalent ways. So one is you take your variety over complex numbers and take the Euler characteristic. Another way is you count points over FQ and plug in Q equals to 1. Turns out the answer is the same. It's a positive integer. For any, so yeah, the upshot of the slide is you start with a bounded affine permutation like this, which we like and understand. You get a positive integer like this, which we, at least the combinatorial audience, likes and understands. So yeah, here's the definition again. And I'm going to give you one important example. So just to give you a feeling of what kind of algebraic varieties I'm dealing with. So if my permutation sends I to I plus k for all I, then this variety is going to, maybe I should write it down. So let me just do an example of k equals 2 and n equals 5. K equals 2, n equals 5. So my variety, lambda 5 squared, is the set of all matrices. 2 by 5 matrices, A, B, C, D, E, F, such that these determinants, so these are k by k determinants labeled by cyclically consecutive intervals. So they should all be 1. So in this example, this determinant here has to be 1. So A has to be minus 1, or sorry, minus A has to be 1. And then this determinant is AE minus BD, it's 1. Next one, BF minus CE is 1. And then the last one is F has to be equal to 1. Okay, so that's my, just, the set of all 6 variables, 4 equations. That is my variety. And you can count, it's pretty easy to count the number of points over FQ. Right? If you just count the number of solutions over a finite field with Q elements, you're going to find, so I did this computation yesterday, so the number of points of this variety over FQ happens to be Q squared plus 1. You just count and you get Q squared plus 1. So, and in general, the theorem is that if the GCD is 1, then the positroid Catalan number you get for this particular permutation is just the Catalan number, or a rational Catalan number. It's the, basically you take, a k by n minus k rectangle, so a 2 by 3 rectangle. And you look at dig paths above the diagonal. So, okay, so we have this mysterious geometric number, and which gives Catalan numbers, and the proof is completely geometric, so it's not combinatorial. But here is a completely combinatorial recurrence for these numbers. So they can be computed by induction, starting with you can remove fixed points, start with n equals to 1. And then the key steps are, first of all, if 2 permutations are C equivalent, then the Catalan numbers are the same. And if the 2 permutations are related by one of those clicking on the green circle, then the Catalan numbers satisfy this recurrence. which looks kind of, I don't know, so F is a single cycle, right? And then you multiply it by simple transposition, so you get 2 cycles, G1 and G2. So it turns out that the recurrence is, Catalan number for F is product of these two plus Si FSI. And the claim is that these two kind of steps, so blue and green moves, basically allow you to compute the Catalan numbers for any affine permutation. And yeah, so let me try to briefly explain. I guess I'm going to run out of time. So yeah, what does it have to do with, five? Oh, 5, okay, I can do 5. All right, so what does it all have to do with dig paths? You know, you have this, like, as Igor likes to say, you know, this is geometry, or this is just combinatorics. So, but in the best possible sense of the word, right? It's really what we like. We can compute everything from this recurrence, and without thinking about any varieties. And so let's compute and see what happens. So it turns out that there is, like, Thomas and I have been playing with this recurrence for a while, and we came up with the following connection to dig paths. So it's going to be slightly technical. To any affine permutation, remember I can associate this vector in the plane, which is n minus k comma k. And so what I'm going to do is I'm going to start with a permutation that's a single cycle, right? And then I'm going to associate to it a collection of points in the plane. And the way it's going to work is, so what I'm going to do is I'm going to pinch every crossing, right? So the length is the number of crossings. So there's 2 crossings here. I pinch the first one or the second one. And each time my permutation splits into 2 cycles. Right? It was a single cycle, now it's 2 cycles. And I only look at the left, so there's going to be 1 cycle that enters from the left and 1 cycle that enters from the right. So I only care about the one that enters from the left. So in this case, and I record the corresponding points in the plane associated to this cycle, this red cycle here, and this red cycle here. And so in this case, so in general, I get a multi-set of points in the plane, which the size of the multi-set is the length of the permutation. So in this case, it happens to be the multi-set of these 2 points. And so the key definition is that a permutation is repetition-free when this multi-set is actually a set. So when there is no repetitions in this construction. So yeah, that's a very strange definition. Right? So, I mean, in this case, we got lucky. There's 2 points, and they're different. So it's a repetition-free permutation. So now, here is the cool part. So I just took a computer and computed all possible repetition-free. Right? So go through all permutation for k equals 4 and n equals 8. There's lots and lots of them. Just write down all repetition-free sets that you get. In turn, you get these 5 sets. And I don't know how good you are at pattern recognition. Like, it took us months to figure out like what separates these sets from other subsets of this rectangle. Which, yeah, like what's special about these dig paths? No, the number is not Catalan. Yeah, the number of such pictures is not Catalan. This is 5 is a coincidence in this case. But yeah, if I had like an extra month of talks, I could let you try to figure this out. But so let me put some kind of suggestive shading here. So these 5 pictures, it turns out that, so it's a theorem that this set of pictures that you get is precisely the set of convex, centrally symmetric polygons inside the rectangle, which is, neither convexity nor central symmetry is at all clear from the definition. This is, we couldn't believe what we saw. Like, I mean, but this, if you don't expect convexity, it's really hard to guess when things are convex. But that is true. So, so for repetition-free permutations, it turns out that the answer is the number of dig paths above the corresponding convex set. And so that's repetition-free is a nice class where we can compute, we can have a combinatorial interpretation in terms of dig paths for the positroid Catalan number. And so going back to the recurrence, this recurrence now has a very particular meaning. So if you take a convex set, you try to add an extra pair of centrally symmetric points to it to keep it convex. Then all dig paths above this either pass through this point, in which case they factor into two smaller dig paths, or they don't pass through this point, in which case they correspond to the second term in this recurrence. So that's the end. Thanks so much.